There is a boundary at the edge of our solar system that took humanity's greatest machine 41 years to reach. Scientists had mapped it, modeled it, argued over it for decades. They believed they understood what it was, how it behaved, and what existed beyond it. They were wrong. Not slightly wrong, not approximately wrong. Fundamentally, completely dangerously wrong. Voyager 2 crossed that boundary, and what it found on the other side did not just surprise scientists. It shattered the models they had spent generations building. And nobody is talking about what that actually means for the rest of us. Something is wrong with the edge of our solar system. Not the kind of wrong that scientists quietly correct in a journal paper and move on from. The kind of wrong that forces an entire field of astrophysics to sit down, look at decades of theoretical work, and ask the question nobody wants to ask out loud. What else did we get wrong? In 1977, humanity made a decision that would define our species. We built 2 spacecraft, not much larger than a family car, loaded them with gold-plated records containing the sounds and images of Earth, pointed them toward the outer planets, and launched them into the void. The mission, at the time, was relatively modest in its ambition. Fly past Jupiter, fly past Saturn, take some pictures, send some data back. Nobody seriously believed those 2 machines would still be operating nearly 50 years later. Nobody seriously believed they would travel far enough to cross the edge of the solar system itself. And nobody, not a single scientist in 1977, fully anticipated what Voyager 2 would find when it finally got there. The boundary Voyager 2 crossed is called the heliopause, the point where the hot, tenuous solar wind that streams outward from the sun meets the cold, dense interstellar medium flowing in from the galaxy beyond. Think about what that means for a moment. The sun, our star, has been blowing a continuous wind of charged particles in every direction for over 4.5 billion years. That wind travels at incredible speed. It pushes outward, past Mercury, past Earth, past Mars, past Jupiter and Saturn, past the orbit of Pluto, past every planet and moon and asteroid and comet in our solar system. And then, eventually, it stops. Not gradually, not slowly. Voyager 1 discovered that the supersonic wind of superheated ionized plasma does not gradually dissipate over distance. Instead, there's a sharp boundary, a definitive edge, where the solar wind meets the interstellar winds from supernovae that exploded millions of years ago. That edge is the heliopause. And until Voyager crossed it, everything scientists thought they knew about it was built on theory, on models, on educated guesses, not on data, not on direct measurement, on guesswork dressed up in sophisticated mathematics. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. But there was a critical problem. Voyager 1's plasma instrument had stopped working after its encounter with Saturn in 1980. That meant the single most important instrument for understanding what actually happens at the heliopause, the tool designed to directly measure the temperature, density, and behavior of the plasma at the boundary, was dead. Scientists could see that Voyager 1 had crossed the boundary. They could confirm it through other instruments, but they could not feel it. They could not touch it with the precision the plasma instrument would have allowed. They could not measure the temperature of what existed beyond. They were, in the most literal sense, flying blind. And here is where everything changes. Voyager 2 carries a working plasma instrument, one that would provide first-of-its-kind observations of the nature of this gateway into interstellar space. When Voyager 2 crossed the heliopause on November 5th, 2018, it was not simply the second spacecraft to leave the solar system. It was the first spacecraft in human history capable of directly measuring what the heliopause actually is, not what our models said it should be, not what our equations predicted, what it actually physically is. The difference between those 2 things turned out to be enormous, and the gap between what scientists expected and what Voyager 2 found is a gap that should make everyone deeply uncomfortable. Let's start with what the models predicted. For decades, the theoretical picture of the heliopause was reasonably coherent. Scientists believed the boundary would be relatively gradual, a smooth transition zone where solar influence faded and the interstellar medium took over. They believed the magnetic field on the inside of the heliosphere and the magnetic field on the outside would be oriented in different directions, that you would cross the boundary and find the galactic magnetic field tilted at a different angle than the solar magnetic field, a clear marker that you had truly left one domain and entered another. They believed the temperature of the interstellar medium just beyond the heliopause would be relatively low, consistent with the cold, ancient material between stars. They believed the heliopause itself would behave differently depending on the current phase of the solar cycle, expanding when the sun was active and contracting when it was quiet. And they believed the 2 Voyager spacecraft, traveling in completely different directions, crossing the boundary at different times in the solar cycle, would cross the heliopause at very different distances from the sun. Every single one of those predictions was wrong. The two Voyager spacecraft confirmed that the magnetic field in the region just beyond the heliopause is parallel to the magnetic field inside the heliosphere, not perpendicular, not rotated at some dramatic angle that would signal the transition from one cosmic domain to another. Parallel. The magnetic field outside the solar system is aligned with the magnetic field inside it. When Voyager 1 first detected this, scientists were confused but cautious. It could be a coincidence. It could be a quirk of the specific location and time of Voyager 1's crossing. With Voyager 1, scientists had only one sample of these magnetic fields and couldn't say for sure whether the apparent alignment was characteristic of the entire exterior region or just a coincidence. Voyager 2's magnetometer observations confirmed the Voyager 1 finding. The two fields align. This is not a coincidence. This is a structural feature of the boundary that nobody predicted and nobody fully understands. Think about what that means. The magnetic architecture of interstellar space near our solar system is connected to, or at minimum aligned with, the magnetic architecture inside it. The boundary is not the clean break scientists had drawn on their theoretical maps. Something else is happening at that edge, something the models cannot yet fully explain. But here's where it gets worse. Researchers now know that the interstellar magnetic field is about 2 to 3 times stronger than expected, which means, in turn, that interstellar particles exert up to 10 times as much pressure on our heliosphere than previously thought. Read that again carefully. The pressure being exerted on the bubble that protects our entire solar system, the heliosphere, the magnetic and particle shield that deflects the most dangerous radiation in the galaxy, is 10 times more powerful than our models assumed. Our sun has been holding back something far more aggressive than we calculated. The heliosphere is under greater stress than we ever knew. And the only reason we know this now is because a spacecraft built in the 1970s managed to survive long enough to tell us. There is a thin comfort in knowing that the heliosphere is still holding. But there should be very little comfort in the realization that our most fundamental models of it were off by a factor of 10. Now let's talk about temperature, because this is where the data gets genuinely alarming in its implications. On the other side of the heliopause boundary, the interstellar medium was found to be at least 54,000 degrees Fahrenheit, significantly hotter than expected. Scientists had anticipated cold. They found fire. The space just beyond the heliopause boundary, where the temperature jump occurs, lies within what NASA classifies as interstellar space. And both Voyager spacecraft hit what amounts to a blazing thermal wall at the edge of our solar system. The boundary is not a soft transition. It is a shock, a thermal shock, a place where temperature spikes in a way that challenges current models of how energy is distributed and transported across that boundary region. The VLISM, the very local interstellar medium, was found to be variable near the heliopause and hotter than expected. That word, variable, is important. Scientists expected consistency. They expected a relatively uniform environment on the other side of the heliopause, something they could characterize and model. Instead, they found variability, movement, fluctuation. The interstellar medium beyond our solar system, at least in the region where Voyager 2 is operating, is not a static, dead ocean of ancient gas. It is dynamic. It responds. It changes. And we do not yet know why. Voyager 2's plasma experiment observed the heliopause crossing from the solar wind into the very local interstellar medium on November 5th, 2018, at a distance of 119 astronomical units from the Sun, a plasma boundary region with a width of 1. 5 astronomical units was observed before the heliopause itself. The plasma in this boundary region slows, heats up, and becomes twice as dense as typical heliosheath plasma. That 5 astronomical unit transition zone, roughly 140 million miles of compressed, heated, densifying plasma, is not something the models had predicted with any precision. The heliopause is not a clean line. It is a zone of compression and transformation, where the solar system spends its last energy pushing against something far more powerful than anyone had modeled. And then, on the other side, within what should be the quiet interstellar void, things get stranger still. As Voyager 2 moves farther and farther from the Sun, the density of space is increasing. The interstellar medium is getting denser the further out the probe travels, and it is not clear what is causing it. Voyager 1, which entered interstellar space in 2012, detected a similar density gradient at a separate location. Voyager 2's new data showed that not only was Voyager 1's detection legitimate, but the increase in density may be a large-scale feature of the very local interstellar medium. 2 spacecraft, 2 completely different trajectories, 2 different directions through space, both detecting the same unexpected thickening of the medium around our solar system. That is not noise, that is a signal. Something is out there, near the boundary of our solar system, that is denser than it should be, and it is surrounding us. The most striking geometric revelation, the one that stopped scientists in their tracks and forced a complete reassessment of heliospheric models, was the crossing distance itself. Both Voyager spacecraft crossed the heliopause at almost exactly 119 astronomical units from the Sun. One crossed during a period of high solar activity, the other crossed during a period of low solar activity. They crossed in completely different directions, different hemispheres of the heliosphere, and they crossed at essentially the same distance. Scientists had predicted the boundary would move as the Sun breathed through its solar cycle, expanding and contracting over the 11-year period of solar activity. That was one of the foundational assumptions in heliospheric models. Scientists expected that the edge of the heliosphere could move as the Sun's activity changes. The big surprise was that the two probes encountered the heliopause at about the same distance from the Sun, even though one occurred at high solar activity and the other at low activity. This should not have happened. According to the models, it could not have happened. And yet, there it is. The data does not lie. The models do. What this tells us is something profound and unsettling. The shape and size of the heliosphere, the bubble that has protected life on Earth since the first organisms crawled out of the primordial ocean, is not controlled primarily by the Sun's activity cycle. Something else is setting that boundary. Something external is holding it in place. Something in the interstellar medium itself is pushing back against the heliosphere with sufficient consistency to maintain its distance from the Sun regardless of whether the solar wind is strong or weak. We are, in a very real sense, contained, and we did not know it until Voyager told us. Now consider the broader implications of that realization. The heliosphere is not just a conceptual boundary. It is, functionally, a radiation shield for the entire inner solar system. The heliosphere has long been considered a shield-like cocoon, protecting Earth and the other planets from the most severe radiation of deep space. Galactic cosmic rays, high-energy particles generated by supernovae, black holes, and other violent cosmic events, are partially blocked by the heliosphere. The more compressed and healthy the heliosphere, the better that shielding. The weaker or more permeable the heliosphere, the more of that radiation gets through to the planets inside. And what Voyager 2 found raises a question that should be asked far more loudly than it currently is. How permeable is the heliopause, really? The answer, based on the data, is more permeable than we thought. Voyager 2 confirmed that the heliopause is a leaky border, and the leaks go both ways. Before Voyager 1 passed through the heliopause, it zoomed through tendrils of interstellar particles that had punched into the heliosphere like tree roots through rock. The boundary is not a wall, it is a membrane, and it leaks. Interstellar particles are finding their way in. Solar material is leaking out. The two environments are interpenetrating in ways the clean, theoretical models never accounted for. Voyager 2 discovered that the solar bubble can be leaky, with solar plasma flowing about 100 million miles past the heliopause, whereas Voyager 1 detected hardly any material leaking out. The two spacecraft found different behaviors, in different directions, suggesting the heliopause is not uniform around the solar system. Different parts of the boundary are behaving differently. Some regions are leakier than others. The shield is not uniform. It has weak points. And there is more. Voyager 2 detected a magnetic boundary just inside the heliopause with powerful magnetic fields, a layer of concentrated magnetic force, compressed and intense, existing on the solar side of the boundary. A structure that models had not predicted, that serves some purpose we do not yet fully understand. Is it a reinforcement mechanism? Is it the Sun's last defensive barrier? Is it a product of the collision between solar and interstellar magnetic environments? Scientists have hypotheses. They do not have answers. The boundary of our solar system contains a magnetic feature that we discovered entirely by accident, because a 40-year-old spacecraft happened to still be functioning when it arrived there. In the last several years, the spacecraft's measurements of magnetic field strength and plasma density have spiked. That suggests Voyager is exploring an unknown region of space. The unexpected measurements may be related to the Sun's activity. And although it is widely accepted that both Voyagers have entered interstellar space, work is ongoing to understand exactly where that boundary truly is. The definition of what boundary the craft passed is still being written. Stop and absorb that. A machine we launched in 1977 has now been in what we call interstellar space for years, and scientists are still writing the definition of the boundary it crossed. We do not have consensus on where the solar system ends and interstellar space begins. We do not have a complete model of the structure Voyager 2 passed through. We detected it, measured it, and confirmed it, but we have not yet fully understood it. The edge of our solar system remains, even now, a zone of active scientific uncertainty. The Interstellar Mapping and Acceleration Probe, known as IMAP, described by its scientists as essentially a vastly more powerful version of earlier boundary sensing missions, launched in 2025 and is designed to capitalize on the Voyager data and provide a far more detailed picture of the heliospheric boundary. This is the next generation of our attempt to understand what Voyager started revealing. But IMAP observes the boundary remotely from within the solar system. It cannot go there. Only Voyager went there. Only Voyager can tell us what it actually feels like to cross that line. Voyager 1 is set to reach a distance of 1 light day from Earth in November 2026, becoming the first human-made object to reach that extraordinary distance. A light day. The distance light itself, traveling at 186,000 miles per second, covers in a full 24 hours. And Voyager will be there, still transmitting, still sending data across a void so vast that the signal takes over 22 hours to reach us. A machine built in an era before personal computers, before the internet, before smartphones, is functioning at the edge of the known universe, and it is still teaching us things. But here's the question that should sit uncomfortably in the back of every mind that understands what this data actually means. If our models of the heliopause, a boundary we have been theorizing about for decades, were this fundamentally wrong? What does that say about our models of everything beyond it? The interstellar medium is not what we thought it was. The magnetic architecture at the boundary is not what we modeled. The temperature is not what we calculated. The pressure is 10 times what we estimated. The density is increasing in ways we cannot yet explain. The data that is coming back from both Voyager probes is pointing toward an unknown region of space whose behavior continues to surprise the scientists analyzing it. And the further Voyager travels, the stranger the data becomes. The current measurements indicate that the interstellar density has increased further from the value it had just outside the heliopause, and no one knows what will happen next. Some theorize that interstellar material may be piling up near the heliopause like snow in front of a snowplow. Think about that image. A snowplow moving through deep space, the heliosphere, our sun's bubble, pushing through the interstellar medium as our solar system travels through the galaxy, and the material piling up at the front. If that is what is happening, then the heliopause is not a static feature. It is a dynamic collision zone. And depending on what our solar system is moving toward, depending on what kind of interstellar environment lies ahead of us in our journey through the Milky Way, the nature of that collision zone could change dramatically in astronomical timeframes. The records Voyager carries, those gold-plated disks with the sounds of Earth, were included on the assumption that some other intelligence might one day find the spacecraft drifting through interstellar space. It was humanity's message in a bottle thrown into the cosmic ocean. What nobody said out loud, at least, not publicly, was that those records were also a kind of acknowledgement, an acknowledgement that we were sending something beyond our understanding, into a region we had never directly measured, across a boundary we had only theorized about. We were throwing the bottle into a sea we had never seen. Now we have seen it, and it does not look the way we drew it on the map. The heliopause is hotter than it should be, denser than it should be, magnetically stronger than it should be, more permeable than it should be, geometrically more uniform than it should be. And the interstellar medium beyond it is more complex, more variable, and more dynamic than our models had any reason to predict. Every instrument on Voyager 2 that can still function is sending back readings that challenge assumptions built over generations of theoretical work. And every answer the data provides seems to generate 2 more questions. There is a moment in every scientific revolution when the data stops confirming the model and starts contradicting it. When the measurements pile up on one side and the theory stands alone on the other, that is the moment when science either advances or retreats into denial. The Voyager data is creating that moment in heliophysics. The models are not holding. The boundary is not what it was supposed to be. The region beyond it is not what anyone predicted. And the implications for our understanding of the sun's protective reach, for our models of how much radiation actually makes it through to the inner planets, for our theories of how life evolved on a world shielded by a bubble we now know is far more complex than we imagined. Those implications have not yet been fully calculated. For 2 decades, the iconic twin Voyager spacecraft have been quietly overturning everything we thought we knew about the boundary between our solar system and interstellar space. Quietly. That is the word that matters. This revolution in our understanding has been happening without fanfare, without headlines adequate to the scale of what is being discovered, without the public attention that discoveries of this magnitude deserve. Voyager 2 crossed a boundary that scientists said behaved one way, and found it behaving in an entirely different way. That is not a minor correction to a footnote in a textbook. That is a fundamental revision of our understanding of where we live in the universe. And what Voyager 2 is still transmitting, even now as it drifts deeper into territory no human instrument has ever explored, carries a weight that science is only beginning to process. Every anomalous reading, every unexpected spike in plasma density, every magnetic measurement that does not fit the theoretical curve, each one is a data point in an argument against our own assumptions. Each one is the universe telling us that the map we drew does not match the territory. The question is no longer whether we were wrong about the heliopause. we were. The data settled that. The question now is, how much of what we believe about the interstellar medium, about the long-term stability of the heliosphere, about the shielding environment of our solar system, and about the cosmic neighborhood our sun has been traveling through for billions of years, how much of that is also built on models that a single spacecraft, still alive against every reasonable expectation, is quietly in the process of dismantling? Voyager 2 is now over 12 billion miles from Earth. The signal takes more than 18 hours to reach us. The power source is fading. The instruments are aging. One by one, over the coming years, they will go dark. And when the last signal from Voyager 2 finally falls silent, it will leave behind a data set that scientists will be analyzing for generations, a record of a boundary that was not what we thought it was, protecting a solar system we do not fully understand from a galaxy we have barely begun to comprehend. Something is out there at the edge of everything we know. And what Voyager 2 found when it crossed that boundary is not a reassuring picture of a well-understood universe operating exactly according to our models. It is a reminder that the most important discoveries are not the ones that confirm what we believe. They are the ones that force us to admit that we never fully knew where we were standing. The wall of fire is real. The magnetic boundary was not in the models. The density is rising and nobody knows where it stops. And out there, beyond the heliopause and the cold, dark space between stars, a 48-year-old machine is still moving, still measuring, still transmitting, still telling us things about the universe that we were not prepared to hear. What else is waiting at that boundary that we have not yet measured? What lies further beyond the region Voyager is currently crossing? And what happens when the last probe that can answer those questions goes silent, and we are left, once again, with only the models we now know cannot be trusted? That silence, when it finally comes, will be one of the most consequential silences in the history of human science. Because after that, we will be back to guessing. And we now know, with certainty, exactly how well our guesses have held up before.